Hello and welcome back to Counting Rocks and Introduction to Combinatorics at CSU. Today we're going to be talking about a special type of graph called trees. A tree is a connected graph that doesn't have any cycle as a subgraph. So here's an example of a tree. There's no cycles in the graph. A forest is just any graph with no subgraph as a cycle, and the only difference between these two definitions is that this one is connected and this one does not have to be connected. So here, for instance, is 3 different trees whose union forms a forest. And if it's all connected, then it's just one tree. Now there's actually 2 other ways to define a tree besides the definition we just gave. One is that a tree is a connected graph such that removing any edge makes it disconnected. So you see the green edge here, if we remove that, it would disconnect the tree into 2 parts. And that's because if you disconnect an edge and it was still connected, then you would have been able to make a cycle, say it was connected here. If we disconnected the green, but this part was still connected to that, then there would have been a cycle with the green if we put it back. So it must disconnect when you remove any edge. On the other hand, you can also define a tree as a graph with no cycles, such that adding any edge between 2 vertices that are not connected does form a cycle. So it's sort of a maximally cycle-free graph. The connectedness is what makes it maximally cycle-free, so that any other edge you add, it's going to form a cycle, whereas in a forest you can connect 2 of the connected components and that won't form a cycle. So here's a characterization in terms of a connected graph with a certain property, and here's a cycle-free graph with a certain property, whereas we could also just say it's a connected graph with no cycles. That's the original definition. Now let's introduce some terminology about trees and degrees. So a leaf is a vertex of degree 1, for instance A is a leaf, and there's 1, 2, 3, 4, 5, 6 leaves on this tree, including C. An internal vertex is any vertex of degree at least 2, so it's just a vertex that's not a leaf. So we have this vertex and vertex that I marked B here, and that vertex there, are all internal vertices. And finally, sometimes trees have roots. They don't have to have a root, but you can pick a special vertex to be the root of your tree. What's funny is that the root could be a leaf, like in this case, but we could have also chosen an internal vertex to be a root if we wanted. Sometimes we're going to deal with rooted trees in order to make them oriented or have a special property. Now here's a fact that we proved by strong induction in the strong induction video, but let's look at it again. How many edges does a tree have if the tree has n vertices? Well, a tree with n vertices turns out always has n minus 1 edges. Let's check that on this tree. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, and 1, 2, 3, 4, 5, 6, 7, 8 edges. So there's always one less edge than the number of vertices, and we can prove this by strong induction on the number of vertices. Strong induction involves a base case. You do have to check it for a tree with just 1 vertex, and then there's no edges, and so it satisfies the condition. I didn't write that here. And for the strong induction step, we assume it works for all smaller trees, and then we disconnect the tree. So pick any edge, remove it. We know that disconnects it into 2 parts. Now let's analyze each of the parts separately. So if this part has k vertices and this part has n minus k, then there's k minus 1 edges on the left and n minus k minus 1 edges on the right, the white ones, and then 1 green edge that we had deleted. And so adding them all up, we have k minus 1 plus n minus k minus 1 plus 1, where these 2 follow from the strong induction hypothesis, and you add them all up and you get n minus 1, so it's still true for our tree of size n. And that works for any tree of size n, so that completes the proof. Now let's ask, how many trees are there? That's a really hard question if they're unlabeled, but if they're labeled, there's a very nice answer called Cayley's theorem. There are n to the n minus 2 trees on n labeled vertices, and it's fun to play with. If you look at 3 labeled vertices, the only possible shape of a tree is really just a path on 3 vertices. And there's 3 ways to draw that path if we label the vertices, because one of the edges is going to be missing from the triangle, and that gives us 3 possibilities for which edge that missing edge is. So there are 3 to the 3 minus 2, or 3 trees on 3 labeled vertices, but this works for any n. Now let's look at a very important type of tree that does have a root. So this top vertex is the root of the tree, and this is called a binary tree, where you're going down and left or down and right at each step, and that's what makes it binary, because each vertex has either a left child and a right child, so 2 children, Or it could be a leaf, so you could just stop at a leaf down here and not have it make any more children. This is a very good data structure for storing information. Sometimes you have to make two choices at every step and store that data in some structure, and a tree is a good way of storing that data. What's magical is that if we try to count the number of binary trees that have n leaves, which is sort of like the number of ways of pairing up a bunch of leaves at the bottom in some order, these are actually a Catalan object. So let's count b sub 1. If b sub n is the number of binary trees with n leaves, then b sub 1 is 1, because if you have just one leaf, it's just the root, just the green vertex at the top, and that's it. And then we can make a recursion. What's nice about this object is that there's a left child and a right child of the root, as long as it's at least 3 vertices, or at least 2 leaves. And so then you can split it into a binary tree on the left and a binary tree on the right, because you can think of this child as the root of the new binary tree going down in each case. And so b sub n, the number of binary trees on n leaves, is the sum of b sub k, if there's k leaves on this side, times b sub n minus k, if there's n minus k leaves on this side, summed as k goes from 1 to n minus 1. Why do we go from 1 to n minus 1? Well, because there has to be at least one leaf on this side and at least one leaf on that side. So we can't have k equals 0 or n minus k equals 0. But otherwise, we get this recursion. This looks a lot like the recursion for the Catalan numbers, and let's tie that together because it's not exactly the Catalan numbers, it's a little bit shifted. In particular, we're going to show that b sub n is c sub n minus 1 for n. So we saw that b sub n equals 1 already. That's c sub 0. So for an induction, that's the base case. And this is the recursion, again, that we found on the last page with the combinatorial argument. And the rest of the strong induction proof after the base case goes like this. So we let m be greater than or equal to 0, and let's assume that this claim holds for all things less than or equal to m. So we want to assume bn equals cn minus 1 for all n less than or equal to m. That's our strong induction hypothesis. And then b sub m plus 1 is... Then we want to show the claim for b sub m plus 1. We want to show that that's equal to c sub m. So we do some calculation here using the recursion for b sub n. B sub m plus 1 is b1 times bm plus b2 times bm minus 1 plus b3 times bm minus 2 up to bm b1. That's where it stops. If we use our strong induction hypothesis on all these smaller b's, well, they're all equal to one smaller c. So we decrease the subscript on each of these letters and turn them into c's. And we get c0 cm minus 1 plus c1 cm minus 2 up to cm minus 1 c0, which by the recursion for the Catalan numbers is c sub m. So b sub m plus 1 is the mth Catalan number. And now you try playing with trees. Cayley's theorem says that there should be 4 to the 4 minus 2, or 16, labeled trees on 4 vertices. Can you find all 16 of them? And that's all for today, and I'll see you next time.